we're going to begin to describe the behavior of a function that is graphed by beginning with the end behavior of the function. So today what we're going to do is we're going to describe the end behavior of only continuous functions given its graph or its equation. So we're going to start off by looking at the graphs of these functions and describing them, and then we'll move on to graphing these functions and describing the graphs of the functions. So what we've got are two polynomials here, and they are polynomials, but we want to talk about maybe outlining what some different types of polynomials are before really describing what's going on with these two. So we're going to start by writing down some different polynomials that you're probably familiar with. So our first polynomial is something that you maybe don't think of as a polynomial, but a linear function is a polynomial because we begin a linear function usually by writing x to the first power, right? So we usually don't write that to the first power, but you should know that it's there. Okay, so our second degree polynomial would be a quadratic. Quadratic functions look like parabolas, and we're going to spend a lot of time dealing with them in units that we have coming up this year. But quadratic functions begin with x squared, and then oftentimes what the next term would be beyond that would be x to the first, and then we'd probably have a constant, right? So it's very similar to a linear function, and in order to take a linear function and turn its equation into a quadratic function, you really just kind of have to add an x squared term to the front of it, and then you've achieved that, all right? Another type of function, and you can start to see the pattern here that we could start to talk about, would be a cubic function. So cubic functions, they bend twice, so this is a cubic function. And that would begin with x to the third power and so on, right? Then there would be an x to the second, an x to the first, and probably a constant. And we could just keep going. This would be a quartic function, right? This bends 3 times. And that begins with an x to the fourth, and so on. So now that we know that these are kind of our major polynomial classifications that we're going to deal with in this class, and there are 5th degree polynomials, 6th degree polynomials, and I could have an x to the 15th if I want to. But we can use that to help describe what's going on with these two functions, f of x and g of x. So we got to think about some things that they have in common. And it's okay to point out some obvious things at first, right? They are both polynomials. That's one thing. They also both have some critical features that are the same, right? They both have maximums and minimums. In fact, it looks like there is a relative max that is the same in both of them. So I'm just going to plot a point right here, and I'm going to call it A. And I'm going to say same local max at A. All right, so they've got that in common. It looks like they also have a local minimum in common. And that point actually is more than just a local minimum. It also appears to be the y-intercept of both of our functions. All right, and outside of maximums and minimums, we want to focus on the roots and see if there's anything similar there. It looks like both of our functions have 3 roots. And it looks like they have the same exact roots as well. So both functions have roots at -4, -1, and at 1. All right, now maybe some things that are different. There are a couple obvious things that are different. And first of all, we talked about the different types of functions or different types of polynomials at the beginning of the lesson. It looks like f of x is a cubic function. And cubic functions, as you can see from this basic example of a cubic function over here, cubic functions have a maximum and a minimum because they just bend 2 times. And you'll notice that they can have up to 1, 2, 3 roots. So cubic functions have 3 roots. This function over here, this g of x function, looks like a quartic function. Quartic functions tend to have 1, 2, 3, 4 roots. But our function only has 3. There's a reason for that, okay? So first, I'm going to say that f of x is cubic and g of x is quartic, because that is true. But the reason that g of x only has 3 roots is because of this very unique root right here. This is kind of a weird root that I want to talk just a little bit about. So when you have a root that doesn't behave like most roots, and what I mean by that is usually when you have a root, the function travels right through the x-axis at that point. So even right here on this function, this root is a very average root, right? The function goes right through that point on the x-axis. And that's true of every root in f of x. But here, our function g of x isn't going through its root. It seems to just kind of bounce off of the x-axis at that point. It is still a root, but it's what we call a double root. So I'm going to make a note that g of x actually has a double root at that point, x equals 1. So real quick, I think we should probably define what a double root is, because those are going to come up later this year. A double root is any place where your function bounces off of the x-axis rather than traveling through it, essentially. So feel free to paraphrase that definition. It's just something that we're going to want to look out for in the future. The last major difference between these two functions has to do with the behavior at the ends of the function. So you'll notice that f of x begins increasing, right? When we start this function f of x, it's increasing in value. Then when it hits a, it turns around and it begins decreasing. And then it finishes from b towards infinity by increasing again. So it's increasing, and then it's decreasing, and then it's increasing. G of x similarly begins by increasing. So it increases to a, and then it decreases to b, just like f of x did. But then b increases and stops at this double root. That's another increase, and finishes decreasing. Okay, so g of x finishes decreasing, but f of x finishes increasing. And that's a difference that we really want to pay attention to. All right, so we're going to start to use some much more specific vocabulary when we talk about something like the end behavior of a function. So what I want to do is say exactly what I just said, but I want to say it in math vocabulary. So first of all, I want to focus on this function f of x. What I want to say, and now I'm going to begin from my first maximum value. What I want to say is, starting here, as I travel to the left, my function decreases. Okay, so I'm always going to use the first point of extrema as a reference point. Okay, so as I travel to the left, my function is decreasing. All right, so the way to say that mathematically is, as x approaches negative infinity, right? That's another way of saying as I travel to the left, because when x values approach negative infinity, we're moving to the left on the x-axis. My function, what is my function doing? Okay, well, back to my function here at a. As I travel to the left, my function value is decreasing. So as x approaches negative infinity, f of x also approaches negative infinity. Downward, right? As I move to the left, my function goes downward. Now with g of x, that's exactly the same thing. So what I would say for g of x, when I'm talking about the left end behavior, is as x approaches negative infinity, again, as we move to the left, g of x approaches negative infinity, g of x moves downward. So just like f of x, as I go to the left, my function decreases. As I go to the left, my function decreases. Now what we've just discussed here, all of this stuff, and I'll just kind of highlight this here, this is all the left side of the function. So we're discussing in that space the left-hand end behavior. All right, so this is the left. Now we've got to talk about the right. So you may be able to kind of figure out how we're going to say this. But this time, instead of saying as x approaches negative infinity, we're going to the right. So we're going to say as x approaches positive infinity. So let's come back here to our function f of x. And we're going to go to b, which is our last point of extrema. as we move to the right at the end of our function, my function value increases. So as x approaches positive infinity, f of x approaches positive infinity. So that's the same way as saying on the right-hand limit at the end of the function, as x moves to the right, my function goes up or increases. And now I could go over to g of x and do the same thing. I'm going to go to my last point of extrema, which is right here at this double root. This time, as x approaches infinity or moves to the right, my function is actually decreasing. So the way that I need to say that is, as x approaches positive infinity, as we move to the right, g of x approaches negative infinity, or g of x moves downward. So that's the mathematical vocabulary that I would use to describe the end behavior of the function. And that would just be for the right-hand side. So we've got our right side of the functions, and we've got our left sides of the functions. And we want to make sure that anytime we're talking about end behavior, we're always starting from the first point of extrema and the last point of extrema. So I'm going to make a note of that here. So I know that this is new vocabulary, and it wouldn't be a bad idea to kind of go back and re-watch the section where we wrote down the official way and the mathematical way to outline the end behavior, because when we come into class on Tuesday, I'm going to ask you to determine the end behavior of these two functions after graphing them in the graphing calculator. All right? Have a good weekend. See you Tuesday.